Let's use mathematical induction to prove this summation. So 4, so P of n is equal to 4 plus 8 plus 12 plus dot 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 plus 4n is equal to 4n times n plus 1 divided by 2. So what is the association of this with the natural numbers? Well, if I look at this part right here, then this is equal to 4 times 1 plus 4 times 2 plus 4 times 3 plus dot 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 plus 4 times n, which we already had, and this is sort of a giveaway, which is equal to 4 times n plus 1 divided by 2. So this right here I really could think of as this: 4 times 1 plus 2 plus 3 plus dot 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 plus n is equal to 4 times n plus 1 divided by 2. Well, we've already seen this, right? That the sum of the integers from 1 to n is equal to n times n plus 1 divided by 2. But let's go ahead and finish the proof. But this is the relationship. We've already basically done this. It's just you multiply both sides by 4. So it should still work out, right? So what's our basis step? P of 1 is, what's our first number here? If n is equal to 1, we only do the first one, so it's 4 times 1, which is equal to 4. And using the formula, is right here, then we have 4 times 1 plus 1 divided by 2, which is equal to 4 times 2 divided by 2, which is equal to 4. 4 equals 4, so that checks out. We will assume that P of k is equal to 4 plus 8 plus 12 plus dot 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 plus 4k, which is equal to, let me draw a line here to separate these, 4k times k plus 1 divided by 2. And now P of k plus 1 is equal to 4 plus 8 plus dot 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 plus 4 times k plus 4 times what? K plus 1. Because remember, these are growing each time. 4 times 1, 4 times 2, 4 times 3, 4 times k plus 1, which is equal to 4 times k plus 1 times k plus 1 divided by 2. This part right here is P of k, right? This right here. So I'll replace that with the formula version. Let's put it over here. So 4 times k plus 1 divided by 2 plus 4 times k plus 1. And now I'm going to go ahead and scale it up to save a step. So multiply by 2 over 2. So this is equal to 4k squared plus 4k over 2 plus 8k plus 8, because 2 times 4 would be 8. And so this is equal to 4k squared. I have a 4k and 8k is 12k plus 8. I'll divide by 2. And what does this work out to be? 4k plus 4 times k plus 2 over 2. So this would be 4k squared. That'd be 8k plus 4k is 12k plus 8 over 2. 4k squared, 12k, 12k, 8, 8. All divided by 2. So it's the same. About this one. P of n is equal to 2 plus 6 plus 18 plus dot 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 plus 2 times 3 n minus 1 is equal to 3 to the nth power minus 1. Now, when you're working problems from books, as I've just demonstrated, they sort of give away the underlying pattern if I look down at this. So what is the association to the natural numbers? Well, this right here is equal 2 times 1 plus 2 times 3 plus 2 times 9 plus dot 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 plus 2 times 3 to the n minus 1 power. I'm just looking at this side. And so what is this really? 2 times 3 to the 0th power plus 2 times 3 to the 1st power plus 2 times 3 squared plus dot 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 plus 2 times 3 n minus 1. So if we put in p of 1, right? 1 minus 1 is 0, so 3 to the 0th power, that would be this, is equal to 2. Or excuse me, times 2, right? So there's 2 times 3 to the 1 minus 1 power. And using the formula, two equals 2. So it checks out. P of k is equal 2 times, let's put a dot here to use this for multiplication, 3 to the 0th power plus 2 times 3 to the 1st power plus dot 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 plus 2 times 3 to the k minus 1 power is equal to 3 to the kth power minus 1. And now p of k plus 1 is equal to dot times 3 to the 0 plus 2 dot 3 to the 1st plus dot 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 plus 2 dot 3 k minus 1. That's the p to the k part. Plus, what's the next thing? Well, I replace k with k plus 1. So let's just write here to make sure we have the arithmetic correct. So if we're looking at that part, the 3 to the k plus 1 minus 1 part, well, really it'd be equal to k plus 1 minus 1 is just 3 to the kth power. So 2 times 3 to the kth, right, is equal to, what does the formula say? 3 to the k plus 1 power minus 1. And actually this is incorrect. This should be 3 to the kth power minus 1 down here. Okay. So this is k plus 1 minus 1. So this is our p to the k. So we get that p of k is this. So 3 to the kth power minus 1 plus 2 times 3 to the kth power. So this, if I rearrange all this, I have 2 times 3 to the kth plus 3 to the kth minus 1. And so what does this become? I figured out the 2 plus 1 part, so this is really another 3, right? 2 plus 1 is 3, so 3 to the kth power times 3 to the 1st power is really k to the, or 3 to the k plus 1 power minus 1. And we didn't have to do anything over here to simplify. Those are the same. Okay? So this particular problem is actually an example of what's called a geometric progression. Now, I will tell you different authors may represent it differently depending on how they want to stop the progression. But it's basically of this form. if I have a plus ar plus ar squared plus dot 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 plus ar to the n minus 1 power, that's equal to a times r to the nth power minus 1 over r minus 1. So how's that the same thing as what we had here? Well, what's the part that's factored out? The a's that are here. Well, that's the 2. And this right here, we can think of as a times r to the 0th power, and this is r to the 1st power. So r here is our 3. Now, why does this not have a denominator? Well, okay, if a was 2, and then since r is 3, 3 minus 1 is 2, 2 divided by 2 is 1, so that sort of factors out, leaving behind 3 to the nth power minus 1, which is that right there. So that's what this is. So we could take this, if we wanted to, and show that the geometric progression works out to be this formula right here. Okay? I'll leave that as an exercise for you, but the underlying logic is really the same as what I did here, except now we have a and r to the 0 power right there. Right? So wherever we had 2's, replace them with a's, wherever we have 3's, replace them with r's, and it all works out.